Virtually every project you work on is going to reach the stage known as, why the heck does this thing not work? So if you're at that stage, well, congratulations first of all, because you're just one step away from the, hey everybody, look at my wonderful working project. The question is, how do you get there? So hi, my name's Glenn. Welcome to All About Arduino, and this video is about how do you move from that why the heck doesn't this work to the look at my wonderful project stage. So if this video helps you, don't forget to like, leave a comment and subscribe so you can see new videos that I post. Also look for me on social media such as Reddit, LinkedIn, Twitter. Okay, so with that, let's get started. So it doesn't matter if your project is complex or simple like this one. There's always going to be a point where you struggle with the why the heck doesn't it work question. So the technique to resolve that challenge is called debugging. And there's two major reasons why there can be bugs or flaws or faults in your project. And they're mainly hardware and software. There are others like maybe the design is not good, or maybe what you're trying to achieve is impossible. For example, as a time machine, this doesn't work terribly well because time machines are not practical. So this this video is about solving problems on the software side. And what I'm going to do is show you some simple techniques that you can use to apply to solve 99% of the problems that you might encounter, just using what's available in the Arduino IDE. And that seems to be where the majority of more difficult problems seem to occur. So sure, there could be wiring problems, like there could be a loose connection. You might have put something in like an LED around the wrong way, or put the chip in the wrong way, or missed a resistor or something like that, or a component value was wrong. But those can generally be resolved by sort of just double checking the components, the values, the orientations, making sure everything's connected up, you don't have shorts and things like that. And you can always refer back to the project that you're following or the data sheet, as appropriate. Whereas the software side is a bit more of an intangible black box, especially to newbies, and so that's why I'm going to sort of show you some techniques that we can follow in this video. To make things a bit simpler, I'm going to follow along a guide that I've created on Reddit, which I'll show you in a minute, and I'm going to use this project here, which is a much simpler one. So if you're not a member of Reddit, it doesn't matter. You should be able to access this for free and without needing to sign up. So you just go to reddit.com and navigate to r/Arduino, or in the search bar up here you can just type in Arduino and then find that in the communities. Then to access the guide, which as I said is in the wiki, you can either click on the wiki link here, or in the sidebar down here there's a link to it just here. So you get into the wiki, and then you can click on the navigation to scroll down automatically to this navigation section, or just scroll down manually, it's up to you. Then go to guides, and then introduction to debugging. And this is the guide that I've created. It's fairly long in its prose form, but it's not that onerous to follow step by step. As I said, it's a follow along guide, and this video is loosely based upon following this guide. It's not 100% exactly the same, but very similar. Definitely based on this guide. So there's the circuit. We can see there's an Arduino with 4 LEDs that just happen to be green, just like my circuit. And there's 4 current limiting resistors. Okay, so first we'll start off with looking at what the program is supposed to do. And hopefully you can see that. There's the 4 LEDs, and what they're doing is lighting up in sequence. There's a very brief delay, it's about 100 milliseconds, 125 milliseconds or so between each one lighting up. Then when they're all on, they remain on for about a second, which should be exactly a second, and then they all turn off and the cycle just repeats. So that's what it's supposed to do. But obviously, for a debugging session, it won't start out doing that, and we'll need to figure out how to make it do that. So in order to get started, I've created this code. And this is the buggy code that we'll walk through and fix up. So just simply copy that, go to the Arduino IDE, create a new sketch or program. Then you can just delete all of that and then paste in the sample from this wiki page. and we'll go through that shortly. One thing that I like to do is have my serial monitor go a little bit faster, so I'll change that to 15200. You can leave it at the default if you prefer. Just one thing to bear in mind is that when you do change that, for it to work properly, you need to have the same setting in this little drop-down box down here. So if you set the default, then 9600, or if you want to change it to a faster speed like I did, then 115,200. At the moment, it's not printing any messages. That's why there's nothing in the screen. We'll fix that as we'll change that, as we go ahead. So what we'll do is just quickly upload this one, because it's a new sketch. It wants me to save it. So I think I'll call it Debugging 101. Save. So it'll just go through its sort of process of compiling and uploading. Okay, so it's uploaded, and so we can see the undesirable behavior, which is just, well, nothing really is happening, just all the LEDs are on. So we're now at the stage of why the heck is it doing that, and how can we fix it? Oh, it looks like one wire is about to pop out, so let's push him in. Okay, so let's move on. One of the first things we need to do, and this is a really simple way that doesn't involve changing or doing anything at all, is just go through what we call a desk check, which is where we manually go through the code and just sort of see if there's any obvious errors. Now, as I do this, some of you may pick up some of the errors that are in the code, and that's fine. That's great if you can. Others might not be as familiar with them and therefore not see them. There's also some subtle ones in there that you might not pick up. And so the idea here is to show the technique, not necessarily to sort of have a contest of seeing who can pick all of the problems first. Otherwise, I'll probably win that because I created the problems deliberately for the video. So what I'll do is I'll just reposition everything so we can sort of see what's going on. Okay, so the first step, as I said, is what we call the desk check. So that's just a matter of sort of going through the code and making sure there's no obvious errors, and also just sort of making sure that the algorithm is the way that we want it to be, and there's sort of not some miscommunication between one part of the program and another. Now, this is a fairly straightforward program, so the algorithm is fairly simple, but still it's worthwhile doing it, especially if it's something or if an area of the code that you haven't looked at for a little while. So I'll just go through what the algorithm is supposed to do. So I use a variable that I call count, so there's the count, to basically count upwards starting from 0. When it reaches the various milestones, so 25,000, 50,000, 75,000 and 100,000, it'll successfully turn on an LED. So when it reaches 100,000, that's the final stage. So we turn the last LED on, have a bit of a delay, and then reset everything back to 0, or back to the beginning stage. Okay, so let's just go through it. You can see I've declared a couple of constants, 4 of them, one for each LED. I'm setting the pin mode to output, which is important because we're sending a signal to the LED. It's an output, so that all looks reasonable. I'll just double check that the LEDs are connected to there, which I think we can assume they are because they all turned on. So that the LEDs should be connected to pins 2, 3, 4 and 5. And it's a bit hard to see on that angle, but that's 0, that's 1, then 2, 3, 4 and 5. So that looks okay. We've got the ground connected, obviously, otherwise any of them wouldn't light up. So that sort of covers the electrical side of it. And then we have our loop. So we can see, as I said before, when the count is at certain values, it'll turn on different LEDs. It looks like it's turning on the correct ones. So that seems reasonable. That's the last one. And one thing we can notice here is when we get to 100,000, we don't seem to be resetting the counter back to 0. So that's an example of the sort of thing that you might pick up in a desk check. You can say, well, it's never really being reset to 0. You might argue that it's being done there, and yes, that's true, but that's not the correct place, and we'll actually look at this line a little bit further on, and this is in fact one of the bugs that we're experiencing. So we'll look at that a bit further into the video. So I think that's it for the desk check. If you wanted to fix this now, you could. So you just put something like count equals to 0 there. anywhere in that if block, but I won't do that just now because I want to sort of show some other problems, but that would be one thing that we could fix just from the desk check. So I don't know if you tried setting the count equal to 0 or not. It's probably worthwhile doing to see if it makes a difference. If you didn't try it, that's okay. It's not going to make a difference in this particular stage of the debugging game. So what we need to do is sort of, well, figure out what's going on. So what I'm going to do is print the value of count. And what I'm going to do is print it at the beginning and the end of the loop. Now it's always a good idea to put a label or an annotation so you know what it is that you're seeing in the serial monitor. And also don't forget to do the begin, otherwise nothing will come out. So we've already done that, so that's fine. So I'm going to use an annotation loop in like that. Be a good idea also to put the variable we're printing as well. So we've got the location of the code where we enter the loop, and we've got the value of the variable that we're printing. And so what I'm also going to do is put that at the bottom of the loop. Now when you do this, it's a good idea not just to put random messages in, but sort of have some sort of an idea of what it is you expect to see if it's working correctly. And the reason for that is to have, if you have some sort of expectation of what's going to happen, then you'll sort of be a bit clearer on what's wrong, and you'll also be able to sort of narrow it down a little bit further depending upon what you actually see. Now because what I'm doing in my algorithm, which is back up here, I'm just going to count upwards starting from 0. I'd expect to sort of see that the counter would say 0 and then 1 and then 2 and then 3 and then 4 and so on. And also I'd expect to see that the count would be, so let's say it starts out the first case, I expect that this would print out 0. It's not equal to any of these, so I'd expect the else here to increment it by 1. So when we get to the out, and I just noticed I had an incorrect label there, so when I'd expect to be at this out print, I'd expect a count to be 1. And the next time through, I'd expect the count to be 1, and then when we come out, it'll be 2. And then 2 in, 3 out, 3 in, 4 out, and so on. So let's upload it and see what happens. Okay, so that's very strange. So we're seeing loop in is 0 and then loop out is minus 31,072. The question is, why is it not incrementing? If you can see it, that's great. If not, then what we need to do is just provide or gather a little bit more insight into it. So I think from that it's pretty clear we need to get some more insight into what's going on with this count variable, because that output's pretty strange to say the least. So what we've definitely achieved so far is we've identified a potential problem area, which again is not hard to do because it's such a simple program. But using this technique, if you had a larger program, you can sort of divide the program and conquer it by putting these sorts of print messages through in various key areas of the program, and then sort of see where it looks like it's a bit haywire. Then you can sort of narrow it down and focus on that. So for example, again, it's a simple program, but we've sort of eliminated setup. I mean, that's very, very trivial, so it's not that hard to do. But the point is we've sort of eliminated that, and we can forget about that for now. Similar with these constant definitions. So what I'm going to do next is add some more print routines, or print debug statements in here. But before I do that, I'll just show you a little technique that might make it a little bit easier, and that's to use a macro. So instead of doing this, what I want to be able to do is just say something like debug, and then just print out these. And I don't have a function called debug that does that, but what I can do is, I could create a function called debug. I could create something like this, which takes 2 values. There'll be a little bit of a challenge with that because I'd need to specify them, so I'd have to give parameters. So I could call it label, and I'd need to say const to avoid a problem, and I'd have to do something like int v, and then I could just print those two values out, v for value of course. But the problem with that is if I had a different type of value, like a double or something like that, then we need multiple versions of these functions. So another way of doing it, which is very type independent, is I can create a macro. Now you might have often seen things like, I don't know, button pin. I don't have a button, but this is an example. And you might say something like it's connected to pin number 7, and then you use button pin as opposed to the hard-coded value 7 in your digital reads, or if it was an LED pin in your digital writes. So it's a little bit like I've done here with these constants, level 0 LED, except I've used the C syntax. I won't go into the advantages and disadvantages of that because that's a fairly big discussion on its own. Just take it for now that there's two ways you can define constants. In this case, I don't want to define a button pin. What I do want to define is debug. And it's going to take two parameters, a label and a value. Now note I don't have to give data types for these. This is what's called a preprocessor macro. It kind of works like a global search and replace through the program. And what I want to replace that with is this serial.print label and then serial.print line v. Now you can split it over multiple lines. It's just easier, I feel, to have it like that. And then so what will happen is when the compiler sees this, it'll take that macro and it will actually just generate that serial.print and then the label, which is looping count, and then serial.print line and value. So that hopefully will make it a little bit easier for you. There is another advantage to this because later on I can just I think comment that out, and then I've effectively removed all the debug statements. So obviously we won't do that just yet. Okay, so we've got that message. Now what I'm going to do is add in some more debug messages at the beginning of each if. So again, just referring back to the tutorial on the wiki. I'm going to print a message like that with my new macro, and after each if statement I'll print a out statement. So debug count in 25k, and then I'll do that after the if statement as well. So this time it'll be count out, and then I'll just do the same 75. Now I won't bother with one after this count equals to 100,000 test because I do have this sort of final one where it prints the loop out. But what I will do is put one in here, debug increment, like that. Now again, we should have some sort of a feel for what this is going to do, what we'd expect to see. So again, we sort of see that weird numbering, and particularly this weird minus 331,000 number. But what I expect to see is that initially it should say count 0 coming in, which is happening. So I guess that's one positive thing. Now if it was incrementing, and maybe it is because we're certainly turning the LEDs on, so it seems like it's executing this line of code. But what I expect to see is count going from 0 to 1 to 2 to 3 to 4 and so on, up to 24,999, and then the next time through will be 25,000, so I'd see this count in 25k with 25,000, and then I'd always see this message. This should appear for the 1, 2, 3, 4 and 5 as well as the 25,000 and so on, and then I'd expect to see that for 50, 75 and 100. So let's find out. I'll upload him. So we have an error. That's our error. Expected primary expression before the colon. Oh. We want a dot and a comma, not two dots. Try again. Okay, so what's happening now? So we've got our loop in count as 0, and then we have the in 25,000. So we're getting this one executed, and then it looks like every single time this one's being executed. Then we get our count out 25,000. So then this one is being executed. The next one we get in the count in, it's 50,000, but we've got a sort of strange number there, so that's a bit weird. And then we get the count out. So it looks like it's executing all of these every single time. So that sort of implies there's something wrong with our if. So what I'll do is sort of just pause for a second and let you have a look at it and see if you can identify what might be the problem. And then we'll come back and see if we can work it out. Okay, so how did you get on? Hopefully you had some luck with that. If not, then I'll tell you what the answer is. So again, if we look through our tutorial, we do explain it here. And the issue is this comparison operator. Now, a single equals sign is an assignment. In other words, it will set count to whatever that value is here, which is why we're seeing this 0 suddenly jumping to 25,000, because it comes in as 0 and it just jumps to 25,000 here. Now then the question is, well, why is this if statement being executed and turning the LED on and doing that if it's just an assignment? And the answer comes down to how C and C++ manages conditional or Boolean values. So a Boolean value is a true or a false, and an if looks for a true or a false. And the way C manages, and C++ manages Boolean values is effectively a 0 is false and anything that's not 0 is true. So because we're setting count to 25,000, the result of this expression will be 25,000. And so therefore C will treat that as true, therefore the if will be executed and this debug and the digital write will be executed and it'll turn the LED on. So the solution here is just simply to change all of these to a double equals, which is a comparison operator that doesn't set count or change count in any way. It just compares the current value to 25,000, and if it's equal to 25,000, then it'll execute this. So we just do that for all of these. Now you might want to have another program ready, because what's going to happen now is it's going to spew a lot of data out, and this is going to be almost impossible to read. So what I'll do is I'll open Blink No Delay. Where's that? Examples, Blink. What I'll do is pre-compile it, because the first time you open something and compile it, it takes a little bit longer to compile, because what's happening is it's looking at everything that's used and it looks for common things that are like libraries, and it builds up a reusable module, which makes subsequent compilations a bit faster. So that's done. The way I did that was by clicking the check, or you can just do verify/compile. Okay, so let's upload this one. And we watch carefully, because hopefully we'll see a different result this time. So that's different. Now they're all off. But what we're also seeing over here is that the output is just spewing past. It's actually impossible to read. And that's why it's handy to have this one ready. So I'll just upload him. And while that's uploading, we'll look at the output here. So let's just find a starting point. So the starting point is loop in count. There it is, there's one. So it starts there. So we're getting the loop in count, and now, somewhat positively, we're not getting the count in 25k message. So we're not seeing this message. That means our ifs are now working, because it's just dropping straight through to this count out message. And then it checks for count 50,000. And so we're not getting that debug in 50, we're just getting this out one. So again, it's not going through here. but also it's not doing the 75k one, but it is doing this. It is doing the count increment. So that's good. So count is 0, so we don't want to turn anything on, and we are going down here and incrementing it. So that means that's good. We've solved that problem. And then when we come out, we can see the loop out count as 1. So it has actually incremented. The problem is that next time around it goes back to 0. So that's sad, but we'll see if we can work through that and fix that next. We seem to have fixed the problem with all the LEDs coming on all of the time, but now we've got a bit of a forgetfulness problem, because when the loop is finished, we do increment the variable correctly, but the next time around it resets to 0. So basically we sort of never really get off the launching pad, no matter how hard we keep trying. And so that's a problem, and I think that's the next problem that we need to sort of focus on. So why is it that we're resetting back to 0 all of the time? And so the temptation might be, I should probably just scroll along a bit further so we can see where we're up to. So that's the output that we saw. And so now we've got this forgetfulness thing relating to the count variable. And so we sort of need to focus on that. Now you might argue that the reason it's being reset to 0 is because of that line of code. And whilst technically that's true, that is initializing count equal to 0, that's not the actual problem that we're facing. What's happening here is that count is what's called a dynamic variable. So what that means is, because I've declared it inside the function, first of all, it's only visible within the function, so that's good. I mean, if I tried to have another function down here, I don't know, some void dummy serial.print count, then I can't sort of do anything with it, but more importantly, I can't modify it because it doesn't belong to this dummy function, so we've kind of protected it. So it's good if you can to put these variables inside of here and limit their scope. That's the technical word for its visibility. So I tried to compile or upload that. I should get an error relating to this dummy function. I'll just make this bigger so we can see it. And sure enough, there it is. See, it says count was not declared in this scope. What that means is that we don't have access to that count variable. Now, one solution I could have is I could actually move this outside of the loop. Now, the problem with that is it's going to be visible everywhere. So that means this will now compile, even though this dummy function really doesn't have any rights to accessing count. It will compile. I probably shouldn't have uploaded it, but that's okay. We're not going to call the dummy, so that's fine. But the more important thing here is that it'll compile. All right, see, that's compiled now. It's trying to upload it. So that's actually bad to make everything global if you don't need to. That's sort of a poor programming practice. So we won't do that. And I'm just going to get rid of this dummy function. Actually, I'll leave it there for a little while. Another attribute of this, beyond limiting its visibility to this loop variable, or this loop function, is its life cycle. So because it's limited to use inside the loop, what happens is it doesn't allocate storage for this permanently anywhere. What happens is when loop is called, it says, oh, I need to have this count variable, and so I'll allocate some space dynamically for it on a thing that's a structure called the stack. Actually, it stores it in registers in more modern CPUs, but the point is it's has a temporary life, and so it lives or has existence or life from the beginning of the loop function, which starts here, all the way to the end. And then once we return, or once we've done this statement and printed out its value, we're basically saying we're not interested in keeping count around anymore because we're kind of done with it. It's sort of like a temporary working variable. And so the next time we call count, next time we call loop, or the environment calls loop, it'll come in here and it says, oh, we need to have this variable called count, so I'll allocate one for you and initialize it to 0. When I put it out here, as I said, that makes it a global variable and it's persistent. It doesn't get destroyed and it remains in existence. In fact, we may even see the LEDs coming on. No, we don't. Anyway. The other way we can do it, but also maintain its privacy within loop, is by putting in the word the keyword static in front of it. So what that means is that I'm still going to declare it. It's still only visible inside of loop, which we can see if I compile this now, it should complain. So just let that compile. But also with the keyword as static, it makes it a persistent. So it becomes, if you like, a global variable, but only within the life of the loop function. So there's our error because we don't have it visible. We don't have count visible outside of the loop function. So just get rid of that. And now we should no longer be forgetting what the value of count is. So just restore this here. And I'll upload it again. Oh, in fact, it was working because I just noticed it was spewing out data in the background here. So we'll see that problem again. So again, it's handy to have this blink without delay here to turn that off. Okay, so you can see it's now spewing data again faster than what we can scroll through and read. So I just upload this to stop that. But already we can see it looks like it's remembering the value. So when we, what's our first message? Loop in count. There we go. So here's one. So the previous loop ended with 990, which means we're coming in with 990. So now it's remembered it. We've lost our forgetfulness. We go through the same process. It's not equal to 25k, 50k, 75k. And then we, at the start of the increment, which is here, I'll make this a bit taller so we can see it. Count increment. We can see, where's it gone? We can count increment, there it is. 9 is 990, and then when we exit the loop, which is here, it's 991. So it looks like that's working pretty good now. And then next time around, we've incremented it, and we come out with 991, and then the first time, or back in with 991, and so on, we get to the increment, and then finally when we exit the loop, it's equal to 992. So it looks like it's working just fine. The reason that we don't see any of the LEDs lighting up is because all of this output is making it run so slowly that it's going to take ages to get up there. So it's at 1000, so 16, 12, 30 to approximately get to 1000. Is that? Oh, so I probably need to clear the output. Anyway, you can see that there's just so much data there. It's just, can we even see where it started? Anyway, it's just taking so long. It's going to take forever to get there. So this is the problem where we've got sort of too much output. And so the next thing we're going to do is just remove or reduce that output somewhat. Okay, so to reduce the output, what I'm going to do is I'm going to remove some of these debugging messages. So it looks like we're fairly happy that the counter is working and the if statement is working, so probably don't need these anymore. So I just comment these out. Basically all of these messages that have an out in them. Yeah, I think I'll get rid of that because we can see what the next one is going to be, because when we do the increment we can see 992, then 993, and the next time in it's 993, so that's fine, I think. And also I don't think we really need to see this because we can also see that this seems to be incrementing, which means that this if statement seems to be working, so we should be good. So now, just before I do upload it, let's just rethink what it is that we expect that we'll see. So we'll see loop in count every single time. So that would mean there's 25,000 of them, which might be a little bit too much. And then when it reaches 25,000, if it reaches 25,000, we should see this message. Then if it reaches 50,000, or when it reaches 50,000, this message, 75,000, this message, then 100,000, this message. And then actually it would probably be working fully then. So let's see what we get. But before we do, I don't think we really need to have 25,000 of these. So how can we limit the output of that? I still probably want to monitor the progress, but how can we sort of limit it? So again, referring to this, I've already done one of the steps, which is removing the out messages, but you can see here the solution to that, and that is to use an expression like this. So I'll just type it in first. I don't know why I'm typing it in. I could just copy and paste it, obviously, so maybe you should do that. I just feel like I've achieved something if I type it in rather than copy and paste it. Obviously there's limits to that. If it was a few hundred lines of code, I probably wouldn't be so excited about typing it in. Okay, so what does this do? So what we're doing is, what it's going to do is it's going to print every 1/100th of these messages. And the way it does that is by doing this division. Now that might not look like a division, but this is an integer division operator called the modulus operator, or modulo operator. And what it does is it gives you the remainder when you divide this by that. So the easiest way to think of it is if I said count %2. So if count was an even number, count %2 would give you 0. And if count was an odd number, then count %2 would give you a 1. And the way that works is, let's just say count was 5. Then 5 divided by 2 is 2, but there's 1 left over. So you get the leftover, or the remainder. Now when we make it 100, then let's say count was equal to, I don't know, 42. Or even 242, yes, let's use 242. So when I divide count, which is 242, by 100, I'll get 2, with 42 left over. So this expression, count %100, would return 42, which is not equal to 0, and so therefore it won't print this. But when count reaches, say, 300, then count %100 would be 300 divided by 100, which is 3, and the remainder is 0. So we will get this being equal to 0, and so it'll print these in steps of 100. So what we should see is loop in count 100, 200, 300, 400, 500, and so on. So we'll get 1/100th of the number of messages we were previously going to get. So that's still going to be 250, because there's 250 lots of 100 to get to there, but it's going to be a heck of a lot less than 25,000. Now when count is 0, then 0 divided by 100 is also going to give a remainder of 0, so we should see the count 0 message. So what we should see is these going from 0, 100, 200, 300, 400, 500, and so on. When it gets to 25,000, hopefully we'll see this. When it gets to 50,000, hopefully we'll see that, and so on. So let's give it a try. I might just clear the output of this. Okay, so we're still getting a lot of messages, but we actually have some life over here in our project now, because we've got the first LED on. So that's promising. I'll upload him so we can suppress the messages again. Okay, so let's just scroll back a little bit. I'll go back to the beginning. So there we can see our count starting at 0, goes to 100, 200, 300, 400, and so on. So that bit's working. We're only getting every 100 of them. If you wanted to, you could do count %1000 to get even less. You can use any number you like, count %500, for example. Doesn't matter, just give you when it gets to a multiple of that divisor, then you can it'll print the message. So there's our count 25k. So that means that this message has worked. So we get count in 25k, it prints it out, it turns on the first LED, which is we can actually see in the project, so that's good. But then it kind of goes off the rails after that. So what happens next? Well, it keeps incrementing, 25, so 300, 400, gets to 26,000, 27,000, 28,000, and so on. Skip a few more. Then it gets to 32,700, and then suddenly it becomes minus 32,700. Right, so let's delve into this weird negative number thing. This seems to be a bit of a pattern here, which might be a little bit more complicated to look up and research, but I can explain what's going on here. I'll just scroll down to the next section that we're at, which is about here, so we can see the output transition to these negative numbers. So what's going on here is that any variable has a limit to how much it can hold. So think of it like a calculator, say a 9-digit calculator. You can only hold 9 digits in a 9-digit calculator. So what would that be? 999 million. Anyway, you can only hold a certain amount. You can expand that by doing fancy things like using exponential numbers and so on, and you can certainly do that in C as well. That's what the double and the float data types are for. But we're using integers, so we're limited to just the number of digits that an integer can hold. So I can visualize what's going on here. If we imagine that this is our integer, and for simplicity I've just done a 3-digit numeric display. So it starts off at 0, so it's 0, 0, 0. If I add 1 to it, it becomes 1. If I add another 1, it becomes 2. Then it'll become 3. Then it'll become 4, and so on and so on and so on, until we get to something like 999. So that's kind of like the maximum we can store in here. So what happens if we add another 1 to it? Well, we'd kind of have 1000, but we only have 3 digits, so we can't show the 1 of the 1000. So it kind of wraps around to 0. But that's not all that's happening. So note here that we do have some extra space. So what's happening in our C variable, and I'm going to kind of illustrate here, although that sort of starts to diverge from reality due to the way integers are stored in computers. But what's effectively happening is this little bit of extra space is used for a sign. So what happens when we add 1 to 999? We wrap around to the 0 state, but then we also get this negative sign here. And if we keep adding numbers to it, this is kind of like negative 1000 effectively. Then it becomes negative 999, then negative 998, and so on. And that's kind of what we're seeing in our output. What would be really nice is if we could sort of tell the compiler, well, hang on, we're not really interested in this sign because we're sort of starting at 0 and just counting upwards. Well, it'd be great if we could use this as an extra digit. And we can certainly do that. And then what we'll have is an ability to count to 4 digits. So we'd still have a limitation. We can still only store 4 digits, and we'll look at that shortly. But that's effectively what we're going to do next. So the way that we do that is it's a very simple change. All we have to do is modify the declaration of our variable to an unsigned number. So this only works for integer data types like int, long, and somewhat counterintuitively char. It does help if you spell it correctly, so that would be unsigned, like that. And then what will happen is we're sort of saying, well, we don't really want this negative number. So what should happen in this type of output is it should go from 32,700 to 32,800, 32,900 and so on. So with a bit of luck, we'll get a bit further in our if statements. So that's what we expect to see. Let's give it a try and see what happens. Okay, so where's our blink? What we can see is that we have 2 LEDs lit up now. So we've actually made an improvement. We've halfway there now. So we're definitely getting past the 32,000 mark that we saw before. There's our in 50K message, which is this one. So that's why we're getting our second LED working on. So it's definitely counting up to 50,000. So that's a good sign. And then what's happening is at about 65,500, we're getting the same problem. At least it's not going negative now, so the unsigned thing is working, but we are resetting to 0. So we're seeing this problem where we're getting to 9999 and we're resetting to 0. Except, again, the way computers store integers is a little bit different. So our actual 999 value is 65,565, I think, from memory. So 655. That's not right. 65,500, anyway, whatever it is, we can look that up. There's a link, I'll give a link to integer overflow, which will give you the number ranges. So what we need to do is fix the range. And effectively what that means is it will take our 3-digit calculator or display, and what we'll do is we'll just ask the compiler, hey, give us some more digits. Again, we can do that. It's fairly simple. but there'll still be a limit. Again, we can only, in this case, count to 6 digits. There are techniques you can add more, but this will be all that we need in our case, just to add more precision. And the way that we do that is we just change the data type to a long. And the difference between an int and a long in Arduino or 8-bit systems is that an int has 16 bits. So that's 16 zeros or ones, which gives us our 65,500 and I think 35 it is. Whereas if we have a long, that's 32 bits. So that gives us, if you like, 65,535 goes at 65,535 values, which works out to be over 2,000 million, 4,000 million if it's unsigned. Now, given that we're only counting to 100,000, 4,000 million should be more than enough, so we don't need to do anything else with a bit of luck. So we just try uploading that. And I'll just scroll here to where we are. So change this to unsigned long to for the data type. You can see here it's already going past 99,000. And now we've sort of reached the final problem. We're stuck on 100,000. And the reason for that is fairly straightforward, and that is that we haven't reset the count equal to 0. So just add that in. So again, we've passed 70, 80, 90, there's 100,000, and now it's reset. And we can see that sort of working in the LEDs as they slowly come on. The reason it's much slower than before is because of all of those debug messages, but you can see it's clearly showing the correct output. So to get the final version of the program, what I can do is just disable the debug messages. And so with a little bit of luck, I haven't actually tried this, we can just comment that out. So effectively what's happening there is every time we reference this debug parameter, it's replacing it with that comment. And of course a comment doesn't have executable code, or the compiler just ignores that, and now we have the original working solution. So a couple of things to watch out for. When you do print statements like this, you want to be careful that you don't introduce what's known as side effects. So for example, here we're outputting the value of the counter, and we're also incrementing it. Now we could have done that. So that would increment the counter and output it at the same time. I'll just upload that just to prove that that's actually happening. Of course, I have commented out, haven't I? I don't want to enable all of the others. Well, I'll just comment these out instead. Okay, so we can see that the thing is incrementing, so that's fine. That's all working just great. Now, when I want to get rid of the debug messages, if I comment that out, but say include this one, I should probably add this as well. CNT, oh no, I don't want to do that yet because I want to show the problem. So if I suppress that message, you can see that that's also suppressed the incrementing of the count, because what's happening in this debug statement is that there's a side effect of printing the count but also incrementing it. So when I removed it, what happened is I've now broken the program because I've removed the debug message. So you have to be a little bit careful about things like that, that in your debug messages you don't want to do something like call a function or modify the value of a variable or something like that, because when you finish and you want to clean it up and get rid of all of those debug messages, you then have a problem that you also lose the increment. So you definitely don't want to do things like that. Just upload that again. So now we won't have any messages because I've commented out all the debug statements, but as you can see, the LEDs are now working. So that's basic ideas for how to do debug. It's essentially about homing in on the problem and troubleshooting it, following what the flow of the program is, like we did with these if statements, narrowing it down to the specific problem of, well, why does the if not work, because we had the single equals and things like that. And if you're never sure, you can always add more debug statements. So hopefully that was useful. I've just really touched the surface of debugging. There's lots of other things you can do as well. So here's a few. That's about the limit of what you can do in the Arduino IDE. If you had some special equipment, such as a power debugger, like this one, or an ICE like this one, you can actually do debugging on the chip as well. And with things like debugging on the chip, what you can do is you can actually look at the variables in memory. So if you've ever used a symbolic debugger, you have a symbolic debugger capability. You can set breakpoints, so you can let the program run, and you can say, I want you to stop when you get to this line, or I want you to stop when you get to this line, and then you can change things and things like that. So there's quite a few other techniques that you can use, but that's sort of the easiest one, and in my experience, you can sort of solve 99% of the problems with this type of technique, just as long as you're a little bit careful about not introducing side effects like this one. Okay, thanks for watching. Hopefully that'll help you and get from the why the heck doesn't this work stage to the look at my wonderful project stage. Please be sure to like this video, leave a comment, especially if there's something you'd like to see or suggestions. And don't forget to subscribe so that when I post new content, you'll be notified of the existence of it. And don't forget to look for me on Reddit and LinkedIn. And if you do create a project and get it working, then I'd love to see a Look What I Made post on our Arduino subreddit. And if you can help me out to produce these videos, please go over to Buy Me a Coffee or subscribe on Patreon. So with that, looking forward to see your working projects, and see you next time on All About Arduino. Bye for now.